Hi, our project is on the evaluation of transformers-based reinforcement learning for games. For our project in the EECS 6892 reinforcement learning class in the spring of 2024. I'm Johan Sweldens,
I'm Evan Knobler.
and this is our project.
So to go through our agenda for our presentation, first we'll give a brief overview and description of the project. We'll talk about the summary of the paper that we used that we based the presentation on, project on. We'll talk about our approach and how it differs from that of the paper. And then we'll go through our software implementation as well as a discussion of our results.
So to begin with, our main objective was seeking to replicate the paper transformer-based reinforcement learning for games. Um, this paper effectively tried to utilize a variety of different models in their deep Q networks in their reinforcement learning applications. And our project specifically is going to be comparing the performance of a traditional, very simple DQN and also a transformer-based DTQN, a deep transformer Q network. And what we're going to be doing is going to be keeping, for the most part, the same training hyperparameters for our reinforcement learning models. And we're going to record the different score values and losses for these training runs and then see how they perform when we're actually playing the game. So to begin with, we're going to be doing a simple classic control game, just like the paper does. This cart pull game, as you can see visualized to the right here, which is a very simple four-state continuous game with only two options for actions. But then also we're going to be exploring a different game, which the paper did not. The Atari uh, environment from OpenAI provides a selection of games. So we're going to be examining this breakout game. We can see if these results that were demonstrated with the performances of the DQN and DTQN can be extrapolated to a much more complicated game. The Atari game has a state shape of 210, 163, and 3 being for the three channels of red, green, blue for the images that can actually get fed into the model, and the entire state size of over 100,000 states for that model.
So to give a brief overview of the paper that we used, so this paper aimed to train several neural networks to play cart pull, specifically using an actor-critic reinforcement learning method. So this included training a deep Q network, a deep recurrent Q network, and a deep transformer Q network. And you can see two of these on the right side. So we see the DQN, which is simply a three-state space through a neural network that outputs the Q values, and then a DTQN architecture on the right side, which is the same state space, three-state space, into a transformer encoder, and then output these Q values. So the paper used the hyperparameters as follows. They used a learning rate of 10 to the -4, used a batch size of 32, discount factor of 0.99, epsilon decay rate of 5 times 10 to the -6, and they ran it for 5,000 episodes. So the goal of this presentation of this project was to keep most of these hyperparameters the same, but we'll talk more about that in the results. So some nuance that the paper introduced was, instead of using the typical state space that was provided by OpenAI, they used a different method. So you can see on the right side on the bottom, this is the state space, the observation space of the cart pull game in the OpenAI environment. It includes cart position, cart velocity, pull angle, and pull angular velocity. But instead of using all four of these, the paper decided to just use the cart position and the pull angle as their inputs, and using those inputs from the current state as well as the previous states to create some sort of recursion. And we'll talk more about this later and its performance compared to using all four states as an alternative. So overall, the paper found that the DQN outperformed the DTQN.
So to begin with, our approach is both similar and different to the approach that the paper followed. So to begin with, we actually added, like I said earlier, the Atari game, which is visualized to the right. we implemented the Atari game as well instead of just the card pull game. However, we still want to keep the exact same models that the paper had implemented. So we kept, as we'll go over later in our code, it's pretty much the exact same representations of those models. However, when we started to explore the Atari games from OpenAI, the actual inputs that these games provide you are very large images. They aren't just deterministic state spaces. So in order to try and maintain the same architectures, we flattened the Atari game, which is not normally a traditional approach for trying to um, work with like image data, but we want to maintain that same principle. Additionally, their paper also introduced and examined the DRQN, which is the deep recurrent queue network. And we decided to not explore that option since we want to mainly look at the difference between the main interesting effects of using transformer networks and how their attention modules can provide different insights on learning for these games. That seemed to be the main idea of exploration for us. So yeah, we just focused on the DQN, DTQN. Additionally, like we were kind of saying earlier, the state spaces in their approach are actually not fully observable. They removed the velocity states from their card pull game just using the angular position and angular and actual cart position along the x-axis. And then what they did, they kind of simulated the angular velocity and the uh, horizontal velocity of the pole by feeding into their model multiple frames per second and having that model learn from those frames. So effectively, the model is supposed to try to extrapolate velocity by looking at the change in the positions of these states. But that's kind of we felt that was just making it too unnecessarily complicated, and it definitely just limits how much learning can be done. So we removed that and just let the game train on all available state spaces. Additionally, we did some small things like adding features to visualize the game and allow the game to play out so we can provide some great visualizations. But then we, for the most part, use the exact same hyperparameters. So we use the same learning rate, epsilon decay, gamma, number of episodes, since we were trying to replicate the results still as much as possible. And this means that the actual hyperparameters we use for the MLP DQN for the poll game are actually the exact same hyperparameters we used for breakout since we want to keep that consistency. Additionally, we did do some experimentations with biased memory, but for the most part, when we're actually providing our results and doing our main training results to try and replicate their paper, we kept the exact same standardized basic memory recall algorithm. So not to add any other complications.
So we, to keep track of our code, we set up a repository that we both had access to. And this repository included was organized into 8 Jupyter notebooks. And this was separated as follows. So we had 2 games. We had the cart pull game, the breakout game. We had 2 networks that we wanted to train for each of these games. This was the DQN and the DTQN. And then for each of these, we also wanted to create a notebook for training and a notebook for playing. So this was 8 notebooks in total. In addition, we created some utility functions that we wrote in Python, and these were used for training, playing, and visualizing the results of the models that we used. And finally, for the models that we used for training, so the DQNs and the DTQNs, we kept the same models that were provided in the original paper. Again, we wanted to replicate the results as closely as possible.
So for example, here, the first network we implemented was the DQN, which is the implementation that is exactly followed as it was described in their paper. This was a very, very simple model, as you can see here on the right, which is the visualization of how the actual mathematics go behind their model. It's very simple. There's no hidden layers. There's no pooling. There's no dropout. There's no regularization. This is a very, very simple MLP. And this is the one that we used for when we're training cart pull and breakout. And we never used a CNN when we're doing the breakout game, the Atari like image game, since we wanted to keep their exact same implementations. As you can see here, Evan, if you click, That is the code for actually describing this model. As you can see, it's very, very simple. It's just two linear layers, which just go by the number of inputs, 128 units, and then the number of outputs. And then these models are initialized, the weights are initialized with the Xavier uniform distribution, as it was described in the paper, and we replicate that again. And overall, this is just a very, very simple model, very simple MLP for trying to do some learning.
And as for the GTQN, we also used a very simple model that we used from the original paper. So this was implemented using PyTorch. And again, it's a very simple model, so that just implements a transformer. So the transformer is a 64 input node model that uses two heads and has three layers, as you can see in the code. And then after the transformer, the output of this block is inputted into a fully connected MLP. And this MLP has two layers with ReLU activation functions. So again, very simple implementation, and you can see the code for that on the right side.
So to begin with here, we have the results of training the card pull game on the DQN. The graphs here below demonstrate 10 equally sized training runs where we trained for 5,000 episodes on the DQN, and all these DQNs had the exact same hyperparameters from that were prescribed from the paper. And as we're trying to replicate the graphs from the paper, and as you can see, there's quite a bit of noise. The training scores, for example, on the left, really quite start diverging after 1,000 episodes, and they just start going all over the place. And that's replicated in the losses as well, which seem to be very, very noisy. If you click on the next slide. So this graph here is pretty much what the paper did is that they presented this information just in a very much simplified form. So this is still the results from all 10 of the training examples. The shaded area in blue, in light blue, is the area between the maximum and minimum scores at each episode for all 10 runs. So it's just a way to compile and show where this training graph starts spreading out. And the dark line in blue is the mean for all the 10 training runs. So as you can see, on average, the model definitely struggles to train. It mostly just appears to just be dealing with a lot of noise after each episode. So that is something we will show later.
And then as for the results of the pull DTQN, you can see very similar results, mostly just noise. And these actually were similar results that we found from the paper. We found that these scores, although you can see look like they're training at some point, they on average are just not training. And this is also replicated in the actual demo that we have. But you can see that at some point it does spike, which can be attributed to why our results were the way they are.
And as you can see here on the left, we have a demonstration of one of the best results from the DQN training runs on the cart pull. So you can see it does like a relatively good job of trying to keep the stick up. And on the right side is the cart pull with the DTQN, one of the best training runs from there. So overall, these models did do a pretty good job of training and are able to play the game at a relatively good level.
And then as for the results for the breakout, you can see that similar to the paper, our results formed a similar path where they started out at a high score, but then seemed to settle at a low score. But on the right side, you can see that the losses spiked at one point. And this means, and this resulted in when we saved our best results, we were able to save this result, which was the best one in the run. And then you can see this here. So on the left side, you can see the result of training the DQN for 500 episodes. You can see that it starts to play, it launches the ball, and then it moves to the left, but it is unable to score any more points as it finds a local maximum at this point. Meanwhile, on the right side, the DQN training for 5,000 episodes continuously launches the ball, and that's the main thing it trained on to score its first point. but after that, it is unable to move because, again, it finds its local maximum. And this is the results for the same game, Breakout, but with a DTQN. Notice how the results here are actually trained quite well. It starts out at 3, it takes a dip in the middle, but then it actually retrains after finishing its initial exploration and ends up with a maximum score that's greater than the initial. And here's the results here. So again, for the DTQN on the left side, we have 500 episodes. Notice that it tries to move towards the ball, but after it makes that first jump towards it, it doesn't move after that. Meanwhile, on the right side, after 5,000 episodes, it does very well at tracking the ball with the base, the bottom, the moving platform, and is able to follow the ball and score multiple points. So this was the best train overall, the best run overall. So to compare our results with the results of the paper, we found that our cart pull game implementation very much outperformed that of the original paper. We found that our results for cart pull, we were able to keep the pull standing up for over 5 seconds, or for 5 seconds on average. Meanwhile, the paper was only able to keep the pull up for 4.5 seconds on average. So this is likely attributed to the fact that we included all 4 states, all 4 observation states in our neural network input. Meanwhile, the paper only used the 2, as we mentioned before. In addition, for this game, we also tweaked the hyperparameter, specifically the epsilon decay rate, to a smaller rate than the one the paper used. And this is because we found that while training, the epsilon was after 1,000 episodes, it was already at single digits. So we figured that by decreasing the decay rate, we were able to allow for more exploration while training.
So for overall, our conclusions, as we're going to be discussing here, the DTQN did, in general, outperform the DQN. And this was replicated in our results in the cart poll and in breakout. This is a pretty interesting result since it shows that the transformer architecture is a more robust model when it comes to trying to perform reinforcement learning. Maybe it's something to do with the attention modules and how they're able to learn. But overall, it was a very exciting result, and we want to see what we can do in the future by expanding this game, by expanding this learning techniques out to a variety of different games, whether they're more complicated ones like chess or Tetris or Pong, any other type of either simple classic control game with very defined single-digit numbers of state spaces, or more complicated Atari games, which once again require hundreds of thousands of potential states. Additionally, we want to try potentially different techniques on how to incorporate those visual inputs from these games, whether it's a convolutional neural network that's going to be used to do the learning, for example, like the games like the Atari Breakout game, or for example, using like a vision transformer in order to do some of those learning techniques on those games as well. And then finally, we would want to try to do some fine tuning on the hyperparameters. When we were replicating their paper, we mainly just used their exact same hyperparameters. However, sometimes it was frustrating because we wanted the games to learn better, and we felt that if we had fine-tuned them, it would have actually done a better job. But overall, that's our conclusion from our project. And also for references, you can click on our GitHub repository to look at our code and our saved models and training evaluations.
Thank you for your time, and that's our presentation.
Right.